Hello, this video is for Stat 310 Handout 7, Part A, and includes a discussion of pages 10 through 14. Okay, let's go ahead and get started then. So Handout 7 includes a discussion of analysis of variance, but in a blocked design. So this is pages 10 through 14. There's another video for the first 9 pages here. So I'm going to fly down to page 10 here and get started. What we have on page 10 here is our statistical model that we're going to use for a one-way ANOVA with a blocking factor. So this looks pretty similar to the model that we've been working with in Handout 6, with the exception that I now have a blocking factor in this model. So let's talk about y is going to be my outcome. Okay, so that's going to be my, for the example here, that's going to be my reaction time. The mu is going to be the overall effect, so the overall reaction time. So not in regards to any particular alcohol consumption level or not regards to any particular age group. That overall mean is going to be denoted by mu. This B, and we're using the subscript J there to denote the different effects due to the blocks. So here, that is going to be the young individuals, the middle-aged individuals, and the older individuals. So I'm going to have 3 blocks here in this particular design. The alphas, just like before, are going to be the treatment effects. And I'm going to have a treatment effect for no alcohol consumption. I'm going to have a treatment effect for 1 ounce of alcohol consumption, and I'm going to have an effect for 2 ounces of alcohol consumption. So there's going to be 3 alphas floating around as well. So we're going to have 3 B's floating around and 3 alphas floating around. And then the epsilon term here is just the error term or the residual term. The I is going to denote the treatment group here. The J is going to denote what block we're in. And the K is going to denote what replicate we have for that particular treatment block combination. In the example that we presented up above, there was only 1 subject in each treatment block combination. So K, it would be 1 if I were to write out that model for the data that we had up above. It would always be 1 because I only ever had 1 replicate for each block treatment combination. Okay, so let's go ahead. I'm going to maybe go into Jump and show you how to fit this model quick. So here's my data inside of Jump again. We're going to do much of the same as we did in Handout 6. We're going to go Analyze, Fit Model. Bring that into the screen here. My reaction time is my response. That's what I'm trying to compare. And I'm trying to do that across the alcohol consumption levels. But I also have this age effect, right? I want to put that in my model as well. This here is the B, okay? And this here is the alphas in that model. My goal here is to compare alcohol consumption across alcohol consumption levels in the reaction times, in the average reaction times. But I want to adjust out the effect of age. And we do that by blocking here. So let's go ahead and hit Run here. And then this is my standard output that we see or have seen. It has much of the same stuff as Handout 6. So I have this analysis of variance table. We're going to talk about that here. I have my my Tukey HSD stuff here. I have my Dunnett stuff. All of that is going to be the same. Okay. One thing that is different is now I'm going to have an effect due to alcohol consumption that I'm going to be interested in, and an effect due to age that I will have in this model as well. So we'll talk more about those in Part B. Handout 7 Part B is where we'll get into the details of those. All right, let's talk a little bit about, let's get this jump output out of the way and talk a little bit about this overall analysis of variance table. Okay. So that is provided. I'll show you maybe one more time here, I guess. That is provided down on the left-hand side, about halfway down or so is my analysis of variance table here. So that's what we're going to be talking about now. Okay, so a statistical model is certainly built on those sums of squared error terms again. So this table here, the heart of this table are these quantities right here. And if we go back and think about what we did back in Handout 6, much of this is going to be very similar. So the corrected total, the C total column or row here, okay, there was a total of 9 subjects. So that leaves 8 degrees of freedom. And I get a sums of squares total, I get a sums of square total value of 0.1177. Now, how is that obtained again? It is very similar to what we did before. What we're going to look at is how much error was created if I don't worry about the treatment, nor do I worry about the blocking. And what I would do there is just look at each of my outcomes. So these are going to be my reaction times. Look at my y's look at the error of the y's from my grand mean. The grand mean of all of this data here, I guess, is 0.6022. Again, column D here was obtained if I have no regards to what is the alcohol consumption level and what is the age level. Just give me the overall mean, which is 0.6022. And then I'm going to look at how much error there is from this point away from the grand mean, which is about 18, it looks like. It's negative because the reaction time is lower than the average. This one here is going to be about 5 because the reaction time is a little bit higher than the average. So that's about 5. I'm going to get these errors or these residuals. And then I'm going to square them because the negatives will cancel out my positives if I don't square them. I'm going to square them and I'm going to add them all up. That 0.1178, that is that 0.117756 number here. That's where that number is coming from. So this bottom number is what would be the total amount of error in my model, if I did not consider the alcohol consumption nor the age. All right, let's talk about this one here, which is going to be my sums of squares error in my model. That's this one here. The sums of square error is going to be how much error do I have if I use my model fully. So if I worry about what consumption level do we have, alcohol consumption level are we at, and what age are we at. So this one right here, the 0.00711, is what is the amount of error that I have if I look at my model completely, which would have both an effect due to consumption, alcohol consumption, and an effect due to the blocking variable. Now, these are my estimates here, right? So this is going to be my mu. If I'm in the no alcohol consumption group, I can expect my reaction time to drop by about 0.1. If I'm furthermore in the young age group, it's going to drop by another 0.089. So I had one person that was not consuming alcohol and was in the low age group or the young age group. So if I take 0.6, subtract about 0.1, that's about 0.5, and I subtract about another 0.09, I'm going to get down to about 0.41 or so. Okay? That is where this value is coming from. So this here, I can get all this on the screen here. This is showing you for somebody that did not consume any alcohol and were in the young age group, I'm taking that 0.60 minus 0.1 minus another 0.09. And that's where I'm getting that 0.4112. If I want to look at somebody that was in the young age group but ended up consuming 2 ounces of alcohol, then what I need to do, how would I do this with my estimates? I would start at 0.6. They're in the 2 ounce of alcohol, so they're going to go up about 0.0978, so basically up about 0.1. But they're young, so I'm going to adjust that down by about 0.09. So that's going to leave about a 0.61 or so. So let's see exactly what that math does. Overall, I'm adding some reaction time because they took 2 ounces of alcohol, but I'm subtracting some reaction time because they're young. So that's where I'm getting that 0.6110. That would be this observation right here. 2 ounces of alcohol, young group. Their actual reaction time was 0.65. My model said it should be about 0.6110. So I'm off by about 3/100ths or 4/100ths. Okay. I don't know if that's seconds or what, but I'm off a little bit. And then I square that. I'm going to do that for all of my observations. And then I'm going to get the error from that model or from that situation. That's where I'm getting this 0.0071. Now, if I go back up here and look at those, that's the 0.0071. The sums of squares to the model is just how much did this model take away? How much of those errors was taken away from the model? So literally, if you take 0.1177 and subtract 0.0071, that's where we're getting the 0.1106. Okay? That's where we're getting this sums of squares here. Now, let's talk a little bit more. There are two things in my model. I got the alcohol consumption and I got the age or the blocking variable. So I can decompose this sums of squares even further. Okay, so how do we go about doing that? That is where my effect tests are going to come in. So my model again has two separate things in it. The effect due to alcohol consumption and the effect due to my age group. That's my blocking variable. That 0.1106 can further be broken out into what is due to the alcohol consumption and what is due to the age. So you can see that a little bit more sums of squares here is due to alcohol consumption, 0.06, versus age, which has about 0.05 on the sums of squares. So when we're thinking about how much of the errors were taken away from the model, 0.1106, that can be decomposed into these two components. And you can look at, if you want, you can study how we go about doing that decomposition here. Or is it at? It's on the next page, I guess. If you're looking at the treatment effect, what I'm going to do is look at the reaction time for those in the non-alcoholic group. Okay, so the reaction time for the average reaction time for those in the non-alcoholic group are going to be 0.5, it looks like. I'm going to then look at the reaction time for those in the average. I'm going to get the average reaction time for those in the 1 ounce group. So that's going to be 0.47, 0.62, and the 0.73. I'm going to use my model to get these effects here again. That's going to be about 0.6. And then the high alcohol group, the 2 ounce, is going to be about 0.7. So notice that these averages or these estimates here are based on just what alcohol group were they in. So 0.5, 0.6066, 0.7. 0.5, 0.6066, 0.7. That's because I'm going none 1 ounce, 2 ounce. None 1 ounce, 2 ounce, 0.5, 0.6066, 0.7. And then I'm going to get the errors from that. That here, or excuse me, this here is going to be the effect due to the treatment being in the model. And then I have that same quantity down here with the blocking. So now I'm going to be just looking at the young people versus the middle age versus the older age. Okay, and that's going to be the errors that are being left over after blocking. So the variation taken away from the blocking effect is 1178 minus 0.0672, which gives me the 0.05. And for my treatments, I got about 0.06 that's being taken away due to the treatment effect. So that's how this 0.11 gets decomposed into its two pieces. There's 4 total degrees of freedom here. This is a nice balanced design. I'm going to get 2 of those degrees of freedom from alcohol consumption. That's because there's 3 different levels of alcohol consumption, which gives me 2 degrees of freedom. There's 3 different levels of age, right? Young, middle, and old. So that gives me 2 degrees of freedom. You add up these 2 degrees of freedom, and that's where they're getting the 4 here. There are 9 total subjects in my study. So the total degrees of freedom is just going to be the 9 minus the 1. That gives me the 8. And then we have 4 left over for error here. We're not too worried about those degrees of freedom, but that's how those are broken up and decomposed. Once we have the sums of squares, then we can get into the mean squares, which is just this quantity divided by the degrees of freedom. And then eventually we can get the F ratio and the p-value. But that's going to be left for the handout 7 part B. So that does it here for handout 7 part A, the last few pages here, pages 10 through 14. Thanks for listening and have a good night.